So, welcome everyone to our webinar organized by the IEEE IS UOW student chapter. This webinar has the title of Unmanned Aerial Vehicles Wind Design Procedures that will be conducted by Elhassan Abdelhalim from Egypt, from Alexandria University. It's my honor to introduce Mr. Elhassan Abdelhalim, an outstanding graduate of mechanical engineering from Alexandria. He served as the former head of the Aerodynamics sub-team. Currently, he's a team mentor at the Alex Eagles team. Both teams are based at Alexandria University. Regarding highlighting his team's achievements, Alex Eagles team is ranked in the top 3 in Egypt's Innovation Catalyst competition. They won the Best UAV Design Award at the 5th International Competition of Military Technical College in Egypt and have a remarkable success in the SAE International Aero Design Competition in the US. For his contributions to the aero design field, Elhassan has received recognition from prestigious organizations and individuals, including the Engineers Syndicate, Alexandria University, and the Ministry of Higher Education and Scientific Research. So I'm welcoming everyone today in this webinar and welcoming our guest speaker, Mr. Elhassan. So please join me in welcoming Mr. Elhassan Abdelhalim, a remarkable engineer whose passion and dedication for aerospace engineering and innovation are truly admirable. So welcome, Mr. Elhassan.
Ladies and gentlemen, good day everyone. I hope you are doing well. I am deeply appreciative for your kind words and warm welcome. I would like to start by extending my heart-feeling gratitude to the dedicated team behind the organization of this event, including the IEEE student chapter and the ARC Future Grids Training Center, and special thanks to Engineer Mahmoud Khalid for the invitation. With this gratitude in mind, let's delve into our presentation and explore this fascinating topic. As we progress, I encourage you to take notes and write any question you may have, as we will have enough time to answer those towards the end of this webinar. So let's get started. So, what is the unmanned aerial vehicle? Exploring the definition of unmanned aerial vehicle can expose us to various definitions in the literature. Simply put, a UAV is an aerial vehicle that is capable of sustained flight without the need for a human operator on board. Within this webinar, we shall explore diverse application of the unmanned aerial vehicle, delve into some basic aerodynamics to enhance our grasp of wing design procedures, gain insight into our aircraft mission, and ultimately, we will explore the wing design procedures in a simple yet comprehensive manner. Exploring the world of unmanned aerial vehicles, we uncover a range of impactful applications that highlight their significant influence in different areas. From detailed path planning to firefighting and versatile roles such as environmental monitoring, railway inspection, and cargo transportation, UAVs provide us with air superiority. To design an unmanned aerial vehicle, we need to dive into the essentials of the aerodynamics. We need to know more about the forces that affect our airplane in the sky, which is the weight, lift, drag, and thrust force. Starting with the weight, gravity force pulls airplanes toward the center of the Earth. Of course, this force changes during the journey due to fuel consumption. So, to defy gravity, an airplane generates the lift force. This force comes from the airplane's motion in the air and it counters the weight. And as you can see, lift is perpendicular to the plane's path and it's mainly generated by the wing. The third force here is the drag. As the airplane moves in the air, it has a resistive force called the drag force. And factors like the shape of the airplane and the airspeed dedicate the drag force. So to overcome drag, we need thrust produced by the engines. So the thrust power depends on the various factors like engine type, number of engines, and airspeed. And of course, Newton's third law of motion clarifies the action-reaction principle behind this engine thing. With this fundamental understanding, we are primed to explore our primary generator of the lift force, which is the wing. Right? Understanding how airfoils generate lift is essential, as the curved shape of the airfoil causes the air to move faster over the upper surface compared to the lower surface. This speed difference resulting in a change in air pressure, as you can see here. So this is the 3D wing, and this is the section of that wing called an airfoil. So with the lower pressure above the airfoil, this pressure contrast creates an upward force called the lift force, allowing the aircraft to conquer gravity and achieve flight. There is a groundbreaking research paper published last year by Dr. Haytham Taha called a variational theory of lift. This paper predicts the path of the airflow over an airfoil, hence predict the right amount of lift force generated by that airfoil. It simply suggests that the free particle within the airflow will move along a straight line, but if constrained, it will deviate only by the amount that satisfies the constraint. Nature will not overdo it. So basically, the airfoil does not care about anything but to receive the right amount of the airflow in the right direction, which is called the angle of attack. And it's basically the angle between the airflow direction and the main line of the airfoil that called the chord line presented here. So this is the leading edge of our airfoil, and this is the trailing edge. This line here is called the chord line. The angle between the chord line and the airflow is called the angle of attack, and this angle is very important to predict our lift with high accuracy. So, as the angle of attack increases, the airflow gradually becomes turbulent. Once exceeding the critical angle of attack, the flow of the upper surface separates from the airfoil, resulting in something called stall. This stall generates a significant rapid loss of lift force and produce excessive amount of drag and vortices. This is crucial for the aircraft safety, hence the stall will affect our selection decisions as we go through the wing design procedures later on. So there is a difference in the coefficient of lift between the airfoil, as we can see here, and the 3D wing due to what's called the aspect ratio. So what is the aspect ratio? The aspect ratio is mainly the length of the wing, which called wingspan, to the chord. So mainly it's a ratio between two lengths. As we can see, the more we have higher aspect ratio, we will have a similar coefficient of lift to the airfoil. So induced drag refer to the phenomena of the airflow escaping from the normal path, which is from leading edge to the trailing edge, and instead it's going toward a much easier path by rotating from the lower surface to the upper surface of the wing, as you can see here, causing a reduction in the lift force and an excessive amount of induced drag. This induced drag and vortices are fully formed in higher altitude, but once an aircraft is approaching a runway, the vortices are gradually blocked. So this is the aspect ratio. The aspect ratio is mainly the wingspan over the chord. This is the total drag of an aircraft, represented by two types of drag. The first one is the parasite drag, also known as zero lift drag, influenced by various factors such as the aerodynamic shape of the aircraft and the size and frontal area of the aircraft. But the second type here is the induced drag, and it's a pretty significant drag. This is because it comes with the lift generated to the power 2, and as we increase the aspect ratio, we decrease the induced drag. Enough aerodynamics. Now it's time to know more about our aircraft mission as we participated in the aero design competition organized by the Society of Automotive Engineers. Society of Automotive Engineers is an international organization founded in 1905 mainly to solve common technical problems and develop engineering standards. But nowadays, SAE organization is providing a set of various competitions to enhance and develop the skills of engineers in solving real-life problems. So the deputized judges from Lockheed Martin were involved in evaluating different stages of the competition in our aero design competition. Big companies also like SolidWorks, MATLAB, Siemens, and many others participated as sponsors for the event. As we mentioned earlier, SAE competitions cover a wide range of engineering fields. Our team has been participating in the aero design competition since 2013. So the mission of our aircraft is to design an aircraft that can operate from short runways to carry spherical cargo as well as boxed cargo, with some limitations such as maximum wingspan of 3 meter, a maximum takeoff weight is 30 meter, the power limit is 1000 watt, and fiberglass plastics are prohibited except for the landing gear parts. So the design requirements are our starting point. So I want you to think of these requirements as the general constraints that will guide you through the different design phases. And the same applies to any design process for different products such as cars, trains, and so on and so forth. A monoplane with a tricycle landing gear, a propeller, and a conventional tail allow me to introduce our aircraft Uqab, named after our eagle in the national flag. Although I have done the conceptual design for this aircraft, our primary focus here lies on the wing design process, and that's exactly what I'm going to delve into in the next slides. The wing design process is an iterative design process that can consist of four design stages: the conceptual design, the preliminary design, the detailed, and the performance analysis. So, in the right here, you can see the whole process of the wing design procedures. At first, it might look a bit intimidating. However, it's much simpler than it looks. So, don't worry, I will break it down step by step, and you will see how easy the concept is. So the first phase is the conceptual design. Here we take our time to understand the requirements and the mission of our aircraft so we can know what constraints are on the design. So the conceptual design phase consists of selection of the number of the wings vertical location, and the wing plane form shape. Starting with the number of the wings, there are up to three possible configurations: the monoplane, the biplane, and the triplane. Monoplanes are the most common and practical choice in modern aviation. Monoplane was not a common choice in the past due to technical constraints such as limited knowledge about airfoils and material compositions. Therefore, the biplane and triplane wings gained popularity during World War I and World War II, as they offer a large wing area packed into a small wingspan, as you can see here. Eventually, the advances in the technology and aerospace materials led to the decline of this type of wings. Moving to the wing vertical location, there are four types of the wing mounting position, which is the mid, high, low, and parasol. So to select the most suitable one, we can perform what's called the trade-off matrix. And this is the trade-off matrix right here. Starting by listing the criteria we are going to design our aircraft based on right here and affect our selection significantly. These criteria can differ based on the mission requirements and the capability of the manufacturer, of course. Then we give a proper weighting for each criterion, which gives the most critical criterion the highest consideration, as you can see here. So the stability is our main consideration here. So it's going to take zero point 0.3. And you may notice that the sum of this column is 1. So basically, the weighting gives the highest value for the most critical criteria. Then we list our candidate, in our case, the high, the mid, and the low wing. And based on our knowledge and reading in references and papers, we can continue to fill this value in the table. For example, high wing have a higher stability than the other candidates, the mid and the low wing. So it's going to take the highest value, zero point 0.9, compared to the others, 0.75 and 0.55. And we continue to fill up this table until we reach the all valid for all candidates. After filling the table, we multiply the weighting from the first column here with the candidate values. So basically, what we are going to do is multiplying zero point 0.3 with zero point 0.9 and then sum the other line after it, zero point 0.3 and zero point 0.6, and so on till we reach the end of this table to give the total for each and every candidate. And just like that, we can make high informed decision that take in consideration all the criteria that may affect our design later on. So the second selection process that we are need to make is the wing design shape, as it plays a pivotal role in aerodynamics performance. So while the elliptical wing boasts an ideal lift distribution, it has a very complex manufacturing process. Consequently, in selecting the optimal wing shape, each criterion must be carefully weighed, considering both knowledge and manufacturing capabilities to ensure an informed decision. For our case here, we have selected the rectangular wing, and we will deal with its cons later on in the detailed design phase. The following phase, called the preliminary design phase, and it's mainly a cooperation between the wing and the propulsion subteam to determine the total takeoff weight, the wing area, and the required
Recording in
propulsion thrust.
progress.
This can be done based on mission requirement, as we mentioned in the previous slides, such as maximum takeoff distance, and we can use what is called a constraint diagram to help us select the design point. So you can review all the equations here in detail in our paper, which I will mention later on. After applying all constraints, we select our design point with the lowest thrust power required and the lowest wing area. Each equation contains the thrust referred to by the symbol T, the weight referred by the symbol W, and the S here refers to the aircraft wing area. After that comes the detailed design phase, which consists of two selection process. So the airfoil selection and the wingtip device selection. The airfoil is the heart of the aircraft as it affects the overall performance significantly. A pivotal factor in airfoil selection is the maximum coefficient of lift, called CLmax, represented here. As you can see, the peak of the coefficient of lift for each and every airfoil. One might wonder, why didn't we choose the S1123 over the E423? And the reason here lies on the stall characteristics for both candidates. The stall behavior in E423 is very gentle, hence it's safer. and that's the geometry of the E423. So the primary function of the wingtip device is to minimize the induced drag, resulting in enhanced aircraft performance. So it's worth noting that the winglets here can be challenging in manufacturing process, and the Horner does not have a higher impact on induced drag compared to the other candidates. Ultimately, our trade-off matrix reveals that the end plate stands out as the optimal choice for our wing tip device. Moving on to the performance analysis, this is the final phase to check the performance analysis of our aircraft by performing a safety analysis and predict the change in the payload concerning the weather conditions. Here I must give credit to my friend Muhammad Alam. He did this CFD analysis, and as you can see, he did it with high mesh quality to ensure accurate results. The CFD analysis confirmed the predicted performance of our aircraft wing regarding the coefficient of lift, induced drag, and parasite drag. So now we are going to do the last process in our aircraft wing design procedures, which is the prediction payload curve. First of all, why do we need the prediction payload curve? Simply put, the performance of the aircraft is changing with respect to different weather conditions. As you can see here, this is the case because the air density, which is represented in this equation that determines the lift force of our wing, the air density is affected by these weather conditions and hence affect the lifting capability of our aircraft wing. So to estimate the prediction payload curve, we analyze the relation between the weight here and the air density. And as shown in the equation, the greater the density, the better the aircraft performance. So the air density is affected by many parameters such as temperature, pressure, and humidity. And we can detect the air density by using online calculators or any other method. So using the air density, we calculate another term that called density altitude, which takes into account all parameters that affect our performance of the aircraft wing. So density altitude is inversely proportional with both the air density and the aircraft performance. In simple words, the higher the density altitude, the lower the aircraft performance. So the graph shows that if the density altitude is 0, then the aircraft can lift up to 17 pounds. As the condition of the weather go worse, then the density altitude is higher, hence the performance of aircraft to lift payload is lower. So this curve can be used as the guide to select the appropriate payload with respect to different weather conditions during the operation of our aircraft رقاب. And just like that, we have finished the wing design procedures from the aspect of aerodynamics. Then comes the structural design followed by the manufacturing process. And as you can see, we have a pretty strict environment when it comes to manufacturing. Fighting with the wing spar while wearing a safety. Who wouldn't be wearing those? A barbecue party, of course, why not? Studies have shown that academics have an increase in the levels of stress and anxiety. Therefore, it's important to have enjoyable and positive outlets for that stress. So, personally, having fun is an essential part of the journey to make an unforgettable memories and overcome challenges. Now it's time to spare wings. Here is one of our flight rounds in California. The judge ensures that the aircraft is positioned in the starting line to measure the takeoff distance accurately. After 30 meters from this starting point, a second line indicates the takeoff distance limit, as you can see in the upcoming second. Launching the aircraft. Here comes the first green flag, indicating a successful takeoff for the aircraft. A second green flag signals the aircraft has reached the safe altitude of 35 meters, and a third flag right to the end of the runway to indicate the aircraft has reached the end of the runway. Next, the aircraft will head back to the starting point and then have a nice approach to prepare for the landing. Of course, it must land safely within a specific landing area while keeping all parts intact. Nice approach, descending. Not the smoothest landing, but he must land before that second line to count the flight as a successful flight. Our aircraft Uqab has won the first place in the design report and the oral presentation and secured seventh place in flight performance and overall scoring, competing with over 31 competitor teams. These accomplishments stand as a testament to the tremendous efforts of 9 generations since the establishment of our team. This journey would have been immensely challenging without their invaluable contributions, for which I am forever grateful. In a 3-year journey filled with challenges, we managed to publish 2 research papers. The first outlines a step by step approach to designing the aircraft wing, while the second one documents the entire design journey of our aircraft Uqab. For those seeking more in depth knowledge of the wing design procedures or a comprehensive overview of our aircraft Uqab, I will share the link for both papers in the chat. You can definitely check them out. Now it's time for questions. Your engagement is valuable. Please feel free to share any questions you may have.
Okay, thank you, Mr. Elhassan, for this nice presentation. Actually, I'm also from Egypt, but I'm amazed by your presentation. And I know that Alexandria University is one of the best in Egypt, but actually I didn't knew that there is kind of good work, okay, and efficient work students can do with our universities. So I'm very pleased to have you as a guest in our webinar. Okay.
It's my pleasure.
Thank you so much. And now it's time for anyone if he has any questions. If anyone have any questions, you can raise it now, please.
Yes, Daniel.
Yes, please go ahead. Yeah, Daniel has a question. Please go ahead, Daniel.
Yes, I do have a question. There was an excellent presentation, very interesting and very concise. The question I have is that earlier in the presentation, you mentioned the paper that was the variation on lift, I believe, some title similar to that. Yes. Is that one of the cited papers in your chat?
No, actually, it wasn't cited because we did write our 2 published papers way before this paper comes to the light. So we didn't have the fortune to cite it in our work. This paper is way higher than our level in the aircraft designing process because it's mainly discussing the deep knowledge and deep science behind the airflow as it contrasts with the airfoil of the wing. So it might be a bit intimidating to start by reading such a paper.
Well, I appreciate that, Dr. Farid, but I'm very interested in that topic. It turns out there's quite a bit of controversy as to how wings generate lift, which I find surprising in the academic papers. If could you post in the chat that a reference to that paper? That would be super great because I am very interested in that topic.
Of course, I will post it right away.
So I also have a question, Mr. Hassan. My question is about the induced drag. I think when you discussed the induced drag, so I understood that this is something that can badly affect the performance of the aircraft. So
Yes.
this is true?
Yes, this is true. This is the case in the range of low speed UAVs, but conversely, the parasite drag tend to have much bigger effect when it comes to higher range speeds of aircrafts. So in our region, induced drag is the main enemy.
So does the induced drag affect the balance of the aircraft while it's flying, or when it's already flying, so it's get more speed that past this range of speed where the induced drag have a bad effect?
All right. So induced drag has a bad effect in two sides. The first side is that it reduces the amount of lift generated by the aircraft wing, as you can see here. As we have a much lower aspect ratio, the induced drag is much higher. Therefore, the lift of the wing is much lower than the airfoil. That's the first issue. So you lose some of your capabilities to generate lift. That's the first issue. The second issue is that when reducing drag, you are posed challenging situation to the thrust capabilities. Hence, the higher the drag, then the thrust must be higher too. This means you should carry more fuel or higher capacity of batteries, in our case, as we operate with radio controlled aircraft. Also, the lower the thrust you have, the lower the speed ranges you can operate your aircraft with. And this is the main issue of the induced drag. So it affects both the lift capability and the thrust capability.
Thank you so much for answering the question. So anyone else have any questions for our speaker?
Yes, please.
Yeah. Again, Daniel have a question. Please go ahead, Daniel.
Excellent. I do have a question in the equations that you had presented early in the presentation. Was
Yes.
there any indication of the relevance to a pusher configuration or a puller configuration? I have seen that pushers seem to have more efficiency in terms of power or range per kilowatt hour of power. I've never seen any equations though that expose that increase in efficiency. Is that in your equations that can occur?
To be honest with you, I do not have a lot of backgrounds in this area as I merely considering designing the aircraft wing. As I said here, the preliminary design is a cooperation between the propulsion sub-team and the wing sub-team. The decision of taking which path to go, either puller or pusher propeller, is the responsibility of our thrust sub-team. Unfortunately, I do not have enough information to answer this question.
Sure, that's fine. Is that graph, that sort of long flowchart type figure, is that in the design and fabrication of a fixed wing unmanned aerial vehicle reference that you gave us? What I like about your presentation is you had many equations that were guiding your design process. There was a flowchart though,
yes.
And is that all in the same source?
No, it wasn't all from the same source. As I mentioned before, our team has started from 2013. Unfortunately, we do not have an aerospace engineering in our faculty. So we have done all of this basically through self-learning. As a wing designer for 3 years now, I have many challenges to reach most of these equations and approaches to the main design phases of the aircraft, and that's why I have decided to publish one of our papers, which is mainly focuses on the low speed range for designing the aircraft wing. So I can mention all these equations and graphs in the design process. So anyone want to build an aircraft and design the aircraft wing can have much smoother experience with this design journey.
Well, thank you very much for that, Professor, because that's actually a tremendously unifying way of making the design be a step-by-step process for sort of like for the engineers that are not the PhDs that are figuring out the whole process that one has to go through. I just want to be more clear. there was a flow chart that showed like, making decisions points that was going left and right, and you were showing excerpts of it at different. That's the flow chart that I'm discussing, not what's being shown in the presentation.
You mean this, of course, right?
Yes, that part. Yes, is that part of your low Reynolds number wing design for unmanned aerial? Oh, that's wonderful. Excellent. Thank you very much.
Thank you.
So does anyone else has any questions?
Seems like no one wanting to ask. So as we wrap up, I want to express my gratitude to my teammates for their unwavering support through the entire journey, extending beyond this presentation. A special recognition is also due to Salah Thabit and Muhannad Mahmoud for the invaluable contributions that enhance the quality of this presentation. Furthermore, I extend my heart-feeling thanks to the organizers for their effort in bringing this webinar to reality. And last but not least, big thanks to the attendees whose active engagement has truly enhanced this experience. Thank you.
Thank you so much, Mr. Hassan. I just want to say that we also enjoyed actually so much with your presentation. Your presentation was so clear, so deep, okay, and the point, details, and step-by-step equations and steps of the design procedure. So we're very happy to have you in our webinar. And we just have a simple certificate to give to you. So, and I'm asking Dr. Abil Islam, he's the chancellor of our club, to hand this certificate to you. Let's first let me share my screen. Again,
that's kind of you.
This certificate. Yeah, so this is a certificate. So please, Dr. Rabiul, if you can just...
Thanks, Khalid, for arranging this webinar. A special thanks to our presenter, Dr. Hassan, for it.
Thank you.
So, although it is not in my area of expertise, but I enjoyed the presentation. Yeah, interesting. Yeah. So again, thanks, Dr. For presenting this nice piece of work. So this is just a small actually gift or appreciation from our side.
I appreciate.
We hope that in future we will arrange some face-to-face presentation, or we'll meet face-to-face. Thanks again for this presentation. Thanks for your time to present this work.
Thank you all, and I'm looking forward to meet in reality with you.
It's our pleasure.
So, thank you.
Thank you.
Thank you, everyone, for attending this webinar. Thank you, Dr. Abiul, for giving us some of your time. I know you're very busy, but thank you for attending this webinar, and thanks for everyone, for the attendees, and for the people who asked actually really good questions. And thank you once again, Mr. Hassan, for your nice presentation.
It's my pleasure. Have a nice day.
Yeah, thank you so much.
Thank you.
Goodbye, everyone.
Goodbye.